Okay, in this video we're going to talk about measurement. So we're going to start off with the measurement of segments, and then we're going to move on to the measurement of angles. So our first concept, the ruler postulate, says the points of a line can be put into a one-to-one correspondence with the real numbers so that the distance between any 2 points is the absolute value of the difference of the corresponding numbers. Now this is an example of a concept in geometry where I'm not really worried about you memorizing the postulate in this case, or the definition in other cases, word for word. You don't need to know this word for word, but I do want you to understand what it's saying and be able to apply it. So here's what it's saying. It's saying that if you had a ruler, where a ruler is a good representation of a segment, and this ruler is 12 inches, then if you imagine a point every inch, then every whole number along that ruler has its own point. Okay, which aids in measurement. So a couple of symbols here. We've got segment CD here in purple. The length of segment CD, or we can think about it as the distance between the points C and D, can be notated just using those two endpoints, CD by itself with no symbol on top. Okay, so there's no segment bar, there's no line bar, no symbol with 2 points side by side indicates the length of that segment with those endpoints, or the distance between those 2 points. Same thing, it's a number value. Okay, using the ruler postulate, we can say that the absolute value of the coordinate of C minus the coordinate of D is going to give you that measurement. Okay, so if we look at this example, we've got a number line, like you've seen since elementary school, and we've got 5 points on that number line at different numbers. If we wanted to know, for instance, SR, so the length of segment SR, then if we take the coordinate of S, subtract the coordinate of R, and find the absolute value of that, and that'll give us our distance, or our length of a segment. So S is at -3 on a number line, R is at 2, so the absolute value of -3 minus 2 is 5. So the length of SR is 5. Similarly, we can find the length of segment RE. So R is at 2, E is at 5. Find the absolute value of the difference of those two coordinates. And we find that RE equals 3. Okay, next up, the segment addition postulate says if 3 points A, B, and C are collinear and B is between A and C, then AB plus BC equals AC. Okay, so we've got a formula here. So looking at this quick diagram here, we've got segment AC, point B is somewhere on that segment in between. If we were to take this piece here, AB, and add its measurement to the measurement of BC, then we would get the measurement of the whole piece, AC. All right, let's look at an example with some numbers, maybe some variables. Okay, we've got segment GN. Point A is somewhere between G and N. And notice we've got some lengths now. So this length, 3x minus 12, is centered over segment GA. So that's the measurement of GA in terms of x. And segment AN has a measurement of 2x minus 8. So the problem says, if GN equals 60, find the value of x, GA, and AN. Okay, so we can start by using the segment addition postulate. So using this formula, but applying it to this problem where we've got G, A, and N instead of A, B, and C, we get GA plus AN equals GN. Substituting in the values that were given on the diagram and in the problem, we get 3x minus 12 for GA, 2x minus 8 for AN. We can add those together, set it equal to GN, which we're told in the problem is 60. So we've got our equation, we've got one variable in x. We want to solve for x, so going back to our algebra skills, we're going to solve this equation for x. Okay, we're going to group our like terms. So our two x's, we get 3x plus 2x, which gives us 5x. And our two constants, we got negative 12 and negative 8. Added together gives us negative 20. Okay, bring down our 60. We've got 5x minus 20 equals 60. Again, our goal is to get the x by itself, so let's add 20 to both sides. 20 plus 60 is 80, so we get 5x set equal to 80. Divide both sides by 5, x is 16. So we got our x value. So now we can take that x value. We're not done yet. We've still got to solve for GA and AN. We can take that x value, plug it into what we know for our measurements of GA and AN. Okay, so we know GA is 3x minus 12. Substitute that 16 for that x. So plug it in. We get 3 times 16 minus 12. 3 times 16 is 48. Take away 12 is 36. So GA equals 36. Lastly, AN, we know is 2x minus 8 from the diagram. Plug in that 16, do the algebra. AN is 24. Okay, our next term is congruent. Congruent means two objects with the same size and shape. Okay, the symbol for is congruent to is kind of like an equal symbol with a tilde on top. Okay, so that means is congruent to. We'll be seeing this term and this symbol a lot this semester, so get comfortable with it. So, congruent, two objects with the same size and shape. Both of those have to be the same for two objects to be congruent. All right, looking at our number line again with our 5 points. We already found out that SR is 5. IE is also 5. So segment SR and segment IE both have the same measurement. All segments are the same shape. So SR equals IE, therefore segment SR is congruent to segment IE. Okay, so the same size, meaning they have the same length, the same shape, all segments are the same shape, so they're congruent. Here's a couple other examples. The two brown segments we've got here, segment BG and segment NS, they've got their measurements on top. Both are 12 centimeters, so BG equals NS, therefore segment BG is congruent to segment NS. Notice we don't call two segments equal to each other unless they are the exact same segment. Okay, they can be congruent, but if they're two separate segments, then they cannot be equal. Also notice this little tick mark that's on the middle of these two segments. The tick mark notates that they are congruent. So even if we have two segments that don't have a number value measurement with them, but they do have the tick marks, then we know they're congruent. In this case, we've got a pair of tick marks on this segment and a pair of tick marks on this segment. That just shows that these two segments are congruent to each other, but not to these two. So we could have two other segments with 3 tick marks or 4 tick marks. So any other segment with 2 tick marks in this case would also be congruent to these two segments in the same diagram. Okay, our next term is a midpoint. You've heard this one before as well. Midpoint is a point that divides a segment into two congruent segments, maybe a different version of the definition that you've heard before. An example here, we've got segment SM. Point A is the midpoint of SM, and we know that because we've got a tick mark on SA and a tick mark on AM, showing that there are two congruent segments on either side of point A, so A must be the midpoint of segment SM. All right, let's look at an example of a problem using the midpoint. Okay, in this example, it says L is the midpoint of segment DF. They want us to find DL, LF, and DF. Here's our diagram. We've got segment DF. We're told, remember, that L is the midpoint. And we're given two measurements here. DL is 2x plus 1, and LF is 3x minus 4. Okay, since we're told that L is the midpoint of DF, then on our diagram, we can go ahead and put tick marks on those two segments. Knowing that L is the midpoint, knowing the definition of a midpoint says that it divides a segment into two congruent segments. Mark up your diagram. We know segment DL is congruent to segment LF, which implies that their measurements are equal. So let's use some substitution. We know the measurement of DL is 2x plus 1, so plug that in for DL. We know the measurement of LF is 3x minus 4. Plug that in for LF. Now we've got our equation, we've got one variable. We can solve those. So 2x plus 1 equals 3x minus 4. We want all our x's on one side. So subtract 2x from both sides. Add 4 to both sides. We end up with x equals 5. But we're not asked for x, we're asked for DL, LF, and DF. But we can use x to find those three lengths. So let's take 5 for x and plug it into each of our three segments. Okay, so DL from our diagram, 2x plus 1, plug in that 5. 2 times 5 is 10, add 1 to it. We know DL is 11. LF, the other segment, 3x minus 4 is what we're told the length of that is. Plug in 5. 3 times 5 is 15. Take away 4 is 11. LF is also 11. We should have already known that because we know they're congruent. So they should have the same measurement. They're both 11 in this case. Lastly, we're asked to find DF. DF is the sum of these two parts using the segment addition postulate. So 11 plus 11, plugging in their values, we get DF equals 22. Okay, let's move on to angles. An angle is formed by two rays with the same endpoint, where the two rays are called the sides of the angle, and the endpoint is called the vertex. Our symbol for angle looks real similar to a less than symbol, though the bottom is kind of more horizontal. When we name angles, we've got three different methods for naming angles. The first one, the simplest. If we know the vertex, and there are no other angles touching that vertex or using that same point as a vertex, then we can just name it with the vertex. Angle A, this is angle A. Or a second method, if there's a tiny number put into tucked into the inside of that angle on a diagram, then we can just name it that number. Now make sure that you distinguish that from the measure of the angle. Okay, we'll talk about measures of angles in just a bit. Okay, so we can call that angle 1. You'll see angle 1, angle 2, angle 3. This form just makes it easier to name angles on a larger diagram. Okay, our third method, the most common method, uses 3 points and 3 letters. So let's say we know the vertex and we know a point on both sides or on either side of that angle. Then we can use a point on one side, the vertex, and then of any point on the other side to name that angle. So we can name this angle RNG. We can also name it angle GNR. As long as the first letter is on one side, the second letter is the vertex, and then the third letter is on the other side, we can name it using the 3-letter method as well. All right. Next up, the protractor postulate. Okay, I'm sure you guys have seen and used a protractor in either elementary or middle school. It's a tool used to measure angles, much in the same way that a ruler is used to measure segments. And there's also a couple similarities in the protractor postulate as in the ruler postulate, the first one we talked about in this lesson. It's very long and wordy. I don't expect you to memorize it, but I do want you to understand it and be able to apply it. So let's go through it real quick. Protractor postulate says let ray OA and ray OB be opposite rays in a plane. Ray OA, ray OB, and all the rays with endpoint O that can be drawn on one side of line AB can be paired with the real numbers 0 to 180 in such a way that ray OA is paired with 0 and ray OB with 180. If ray OC is paired with some variable x and ray OD is paired with some y, then the measure of angle COD, so the measure of this angle here, our lowercase m in front of our angle symbol, denotes the measure of. We can find that by finding the absolute value of the difference of x and y. Okay, classifying angles. Okay, again, we've seen this since elementary school, but we'll review it because we'll be using it a lot this semester. Okay, let's look at our first one. An acute angle has an angle measure between 0 and 90 degrees. So our symbol for degrees is our little, looks like an exponent, it's a little subscript circle. Okay, where degrees is a certain unit for measuring angles. A right angle has a measure of exactly 90 degrees. This little box or square always denotes a right angle. An obtuse angle is any angle whose measure is between 90 and 180 degrees. And lastly, a straight angle, which looks like a line, is an angle whose measure is exactly 180 degrees. So in this example up here, angle AOB is a straight angle. And lastly, the angle addition postulate. Okay, it says, real similar to the segment addition postulate, but for angles, it says that point B is on the interior of angle AOC, then the measure of angle AOB plus the measure of angle BOC equals the measure of angle AOC. So this postulate just says, if you take this angle here, AOB, and you add it to the measure of this angle here, BOC, then what you're going to get is the measure of this big angle here on the outsides, angle AOC. So in this example, let's say that the measure of angle AOB is 30 degrees, the measure of angle BOC is 75 degrees. We want to find the measure of angle AOC, okay, the big angle. So using our angle addition postulate, let's take the measure of angle AOB plus the measure of angle BOC, our two smaller angles, add them together to get our big angle, angle AOC. So substituting in what we're given in our problem, we've got 30 degrees plus 75 degrees. Adding those two together, we get 105 degrees for the measure of angle AOC. It's not so bad, right? Okay, last example. Using the same diagram, let's get rid of these numbers. This says, what is the measure of angle AOB if the measure of angle BOC is 60 degrees and the measure of angle AOC is 115 degrees? Okay, so using the same diagram but asking the problem in a slightly different way. We're not given the measure of this small angle, but we're given this angle and the entire angle itself. Let's set up our equation the exact same way. We're just going to substitute in different values. So our same equation here, we don't know the measure of angle AOB, so we bring that down. Substitute in 60 for the measure of angle BOC. Substitute in 115 for the measure of angle AOC. And then solve for the measure of angle AOB, just like you would if it was an X or a Y or any other variable. Okay, so subtract 60 from both sides. We get the measure of angle AOB is 55 degrees.